Hello, everyone, and welcome to the European Non-Associative Algebra Seminar. Today, I'm glad to introduce the talk by Simone Blumer from Universitat Vienna, Austria. He's going to talk on quadratically defined the algebras and HNN-extensions. Please.
Thank you very much for the introduction, and thank you for inviting me to this seminar. Today I'm talking about quadratically defined Lie algebras, and I will start by roughly defining what I mean by a quadratic Lie algebra. So essentially, a quadratic Lie algebra is a Lie algebra where the minimal relations only involve simple Lie brackets of the generators. Within the class of all quadratic Lie algebras, you find the class of Kojoule Lie algebras, which are important because they have a good cohomological behavior. In fact, you can compute explicitly the homology ring of a Kojoule Lie algebra just by using elementary linear algebra computations. You may think that, in principle, you can always compute cohomology by using elementary linear algebra computation. But the problem is that in general, you have to compute a lot of kernels and images of maps between usually infinite dimensional vector spaces, and you have to compute infinitely many kernels and images. So yes, in principle, it is just linear algebra, but in practice, it is almost impossible to compute explicitly cohomology. Well, we'll see that in the case of Kojoule algebras, things are much easier, and also passing to the cohomology doesn't lose any information of the Lie algebra. So first of all, I want to outline the contents of my talk. I will start with some more detailed definition of what I mean by a graded Lie algebra and of cohomology of Lie algebras. And then we will study the two main classes of quadratic Lie algebras, which are Kojoule algebras on one hand and blockato Lie algebras on the other. So let's start with positively graded Lie algebras. By positively graded Lie algebra, we mean a ordinary Lie algebra, so that its underlying vector space is graded on the positive integers. For me, a graded Lie algebra will always be graded over the positive integers, and we also want that the Lie brackets respect this grading, so that the Lie brackets between elements of degree I and j is either 0 or an element of degree I plus j. Now, an example of a graded Lie algebra is a free Lie algebra on a graded vector space. And if we fix a homogeneous subspace of a free Lie algebra, then the quotient of the free Lie algebra by the ideal generated by that vector space is a graded Lie algebra. And we will use this symbol on the right to denote the presentation for a Lie algebra. Of course, any graded Lie algebra can be realized as a quotient of a free Lie algebra. Okay, in this notation here, the vector space V is called the generating space, while the vector space X is the relation space. And if V is a vector space concentrated in degree 1, and it has finite dimension, then we will call the Lie algebra a standard Lie algebra. I will use the name standard as a synonym of one generated Lie algebra. And what if also the second space X is concentrated in degree 2? Then we will call the Lie algebra a quadratic Lie algebra. So here, a quadratic Lie algebra is a Lie algebra that is generated by elements of degree 1, and all the minimal relations, all the relations come from relations of degree 2. So by relation that only involve a linear combination of simple Lie brackets between generators. I want to give you some examples that will be important later. And this is an example coming from group theory. And this is the example of a right-angled arc in Lie algebra. So you fix a finite simple graph, so a set V and a finite set V and a set of two-element subsets of V. And we define as a generating space for the Lie algebra the linear span of all the vertices of the graph. And the relations are given by the commutation between the endpoints of each edge. So we have one generator for each vertex of the graph and one relation for each edge in the graph. So the right-angled arc in Lie algebra is the quadratic Lie algebra with this presentation here. Okay, let's see some easy and concrete examples. So if gamma is a discrete graph, so it has no edges, then of course the associated Lie algebra is free. It has no relation. And on the opposite side, if the graph is a single edge, then the Lie algebra is abelian of rank 2 because you have two generators that must commute because they are the corresponding vertices are adjacent in the graph. So the associated Lie algebra is abelian, and then this can be generalized to higher dimensional Lie algebras. And so you see if the graph is complete, then the associated Lie algebra is always abelian. So notice that right-angled arc in Lie algebras somehow interpolate in between the free and abelian Lie algebras. And they are also called partially commutative algebras for this fact here. Okay, so as another example of a graded Lie algebra, right-angled arc in Lie algebras are really well behaved, and later we will see how well behaved they are. On the contrary, Besvina-Brady Lie algebras are usually much less well behaved. They are ill-behaved, I would say, and they are defined as in the group theoretic case as some specific ideals of the right-angled arc in the algebra. So given a RAG L gamma, you can send each vertex to the element 1 of the field, viewing the field as an abelian Lie algebra. And then the kernel of this of the induced homomorphism is called the Besvina-Brady Lie algebra of the graph. Okay, so let's see an example. Here we have a graph that is neither discrete nor complete. So the associated right-angled arc in the algebra will not be free nor abelian. In fact, it has a free factor and it has a central element Z. So we get that the rectangular arc in the algebra is a direct product of a free Lie algebra with an abelian Lie algebra. And in this case, it is not hard to see that the associated Besvina-Brady algebra is generated by two elements, and it is in fact free. In fact, in general, the Besvina-Brady algebra is standard and free if and only if the graph, the defining graph, is a tree. Okay, let's see another apparently easier example. This is the discrete graph on two elements. The right-angled arc in the algebra is, of course, free, and so must be the Besvina-Brady algebra. The problem is that it is not finely generated because it is generated in degree 1 by a single element, and it has, in higher degree, it is precisely the derived subalgebra of the free Lie algebra. So it is not finely generated, and hence it cannot be a standard Lie algebra. In fact, Kokhlukova and Martinez-Perez proved that the Besvina-Brady Lie algebra is standard or generated in degree 1 if and only if the graph is connected. So the first case was connected, so the Besvina-Brady Lie algebra is finely generated and standard, and in the second case, the Besvina-Brady Lie algebra is not finely generated, as the graph is not connected. Okay, so I want to spend now some time about Lie algebra cohomology. I will not give you the whole definition, but I will only stress some important facts about them. So given a graded Lie algebra, we can define a sequence of vector spaces indexed by the non-negative integers that are called the cohomology groups of the Lie algebra. And these groups, or vector spaces, measure somehow the complexity of the Lie algebra. In the graded case, however, each cohomology group is graded itself. So we get a second grading called the internal grading for the cohomology. And we will see that this contains a lot of information about the Lie algebra in the graded context. As usual, one can endow the whole cohomology group, so the direct sum of all the cohomology groups, with a multiplication map called the cup product that makes the whole cohomology group into an algebra, a bigraded algebra indeed. Bigraded means that the product respects both the gradings. And moreover, with respect to the first grading, the so-called homological one, the homological grading, the cup product is graded commutative. So it is commutative up to the multiplication of a plus or minus one. Okay, so nice. Let's see now some properties of the cohomology ring of a graded Lie algebra. So suppose that we have a Lie algebra given with a minimal presentation, so that the vector space V is the minimal possible vector space that generates the Lie algebra, and X is the, let's say, a minimal generating set for the ideal for the relation space. Yeah, okay, so the first and most trivial fact is that the cohomology groups, the bigraded cohomology groups, are concentrated, let's say, above the diagonal. In fact, you can think of these two degrees, these two indices, I and J, as the axis of a Cartesian plane, and the diagonal is precisely the set of cohomologies where I is equal to J. So the first fact is this one. We have that the cohomology is not is zero below the diagonal. Yeah, so the zeroth cohomology group is always concentrated on the diagonal, meaning that the zeroth cohomology group is concentrated in degree 0, and it is in fact always one-dimensional. So it doesn't contain any information about the Lie algebra. The first information that we can get from cohomology groups is from the first cohomology group. The first cohomology group is related with the minimal generators of the Lie algebra, and in the sense that the degree J component of the first cohomology group is isomorphic with the dual vector space of the degree J component of the generating space. So for graded Lie algebras, the dimension of the first cohomology group is equal to the minimal number of generators of the Lie algebra. And moreover, the dimension of each homogeneous component of the first cohomology group is equal to the minimal number of generators in that degree. And similarly, for the second cohomology group, we get a similar situation, so that the second cohomology group is related with the minimal number of relations of the Lie algebra. So with the dimension of the minimal X that produces our Lie algebra. So again, the degree J component of the second cohomology group is isomorphic to the dual of the degree J component of the relation space. Okay, so we want to see some examples, and we take our favorite Lie algebras, which are now rectangle darting Lie algebras, for which things are are really easy. And in fact, we again take this graph here, this line of length 2, and we want to compute its first cohomology group. But we know that the first cohomology group is related to the number of generators of the Lie algebra. fact, you can see that an easy computation shows that the first cohomology group is the linear span of the dual basis of the canonical basis for the Lie algebra. By canonical basis, I mean, in this case, in the case of right-angled Artin Lie algebras, I mean the basis consisting of the elements corresponding to the vertices of the graph. So the first cohomology group is three-dimensional, as the graph has three vertices, or equivalently, the Lie algebra is generated by three elements. And you can see that it is concentrated in degree 1. This because one can endow the right-angled Artin Lie algebra with, as we said before, with a grading so that the generators have degree 1 and the relations are all of degree 2. So we get that H1 is equal to H11. Okay. And the second cohomology group is can be computed in terms of the cup product. And one discovers that each element of the second cohomology group lies in the image of the cup product. And so the second cohomology group, as we may expect, is two-dimensional because we have two minima relations here. And it is also concentrated in degree 2. So we see that both the first and the second cohomology groups are concentrated on the diagonal. Okay, yeah, I underlined here the generator for the second cohomology group, which comes from, roughly speaking, it comes from the first relation here, or equivalently to the first edge, xz. And similarly, the second generator, let's say canonical generator of the second cohomology group is related with the second relation here. One can do more and compute the whole cohomology ring for this easy example of a Lie algebra, and discovers that the whole cohomology ring is generated by the degree 1 component of the cohomology. And in fact, it can be given this presentation in terms of the exterior algebra, lambda. And so let's see a bit what it means. We are generating our cohomology with three vertices, which correspond to the three vertices of the graph. And we have a single defining relation, which comes from the only pair in the graph that doesn't span an edge. So in general, we will see that this is a general phenomenon for right-angled Artin Lie algebras, and the presentation is always of this kind. But anyway, we see that the whole cohomology ring is generated by all the elements of degree 1. Stuart Brady in 1970 introduced the notion of a cojoule algebra. We will only specialize to the case of Lie algebras, but he did this for all associative algebras. Now, a Lie algebra is not associative, but from a cohomological point of view, there is not much distinction between the Lie algebra and its universal enveloping algebra, which is in fact associative. So Lie algebras in the cohomological setting are somehow associative in some sense. Okay, so Stuart Brady defined this class of algebras as he called them homogeneous cojoule. We will call them just cojoule Lie algebras. And a Lie algebra is cojoule when its cohomology ring is generated by its element of degree 1. Okay, so let's see some properties of cojoule algebras. First of all, cojoule Lie algebras are always quadratic. And this is easy to see because they are, of course, standard, so generated in degree 1, because the H1 is clearly H11. And also, it is quadratic. The relations are of degree 2, because the H2 can only be obtained by taking products of elements of degree 1. And the product of the degree of elements of degree 1 is an element of degree 2. And this implies that all the relations that are encoded in the second cohomology group are concentrated in degree 2 by this equality here. So yeah, causal Lie algebras are particular kind of quadratic Lie algebras. Also, I could prove in my PhD thesis that the center of a causal Lie algebra is always concentrated in low odd degrees, which might be odd and weird because apparently, one at first has no idea how to relate the center of a Lie algebra with such a cohomological behavior. In fact, I wanted to prove that the center of a causal Lie algebra is always concentrated in degree 1, but I couldn't, and I also couldn't find any counterexample, so the problem is still open. But anyway, I could prove that, the center is quite small and concentrated in low odd degrees. By low, I mean less than half of the cohomological dimension of the Lie algebra. But anyway, I will not use this fact here. Okay, so as examples of causal Lie algebras, you can think of all right-angled Artin Lie algebras. And this is a famous theorem by Froberg, who actually didn't prove it for Lie algebras, but for their associative counterpart. And he proved something more general. But yeah, we get that all right-angled Artin Lie algebras are causal. So the phenomenon we saw here is not special for right-angled Artin Lie algebras. This is always the case. So good. Okay, I will now discuss about this result of Löffel that allows us to compute explicitly the cohomology of a causal Lie algebra. And so the result says that if we start with a standard graded Lie algebra, so that the vector space, the generating space is concentrated in degree 1, then Löffel gives us a procedure to compute the algebra generated by the elements of degree 1, 1. And first of all, we have the first equality is interesting because the subalgebra of the cohomology ring generated by the elements of degree 1, 1 is equal to the, let's say, the diagonal cohomology of the Lie algebra. So the direct sum of all the diagonal pieces of the cohomology. Okay, and this is quite abstract so far, but he also gave an explicit reformulation of the diagonal cohomology in terms of the degree 2 component of the relation space. So the diagonal cohomology can be computed as the quotient of the dual of the generating space of the Lie algebra by the ideal generated by some orthogonal complement of the degree 2 component of the relation space. So the first interesting fact about this is that if you take two standard Lie algebras with the same generating space and same degree 2 component of the relation space, then their diagonal cohomology are equal because it only depends on the degree 2 component of the relation space. And so you may imagine that quadratic Lie algebras have a special role in the theory of arbitrary graded Lie algebras because of this fact. Okay. And in particular, we have defined causal Lie algebras as Lie algebras where the left-hand side is precisely the whole cohomology ring. So if a Lie algebra is causal, then the two gradings are equal. So there is no distinction between the homological degree and the internal degree. Okay, I want to recap now a bit about our definitions so far. First of all, we have seen that the first cohomology group is related with the minimal generators of the Lie algebra, and if H1 is equal to H11, so if the degree 1 component, if the first cohomology group is concentrated in degree 1, then the Lie algebra is standard. If, moreover, the second cohomology group is concentrated in degree 2, then the Lie algebra is also quadratic. And we can extend this homogeneity property to higher degree, and we get the definition of a Kojoule Lie algebra. So a Kojoule Lie algebra is a Lie algebra where all the cohomology groups are concentrated on the diagonal. And so you can see that given a presentation of a Kojoule Lie algebra, you find an explicit presentation for its cohomology ring. And the computation you have to perform is just computing a kernel between a map between finite dimensional vector spaces. And it is pretty easy to do. Okay. Okay, this is Froberg's theorem in the general setting of rectangle arcing Lie algebras, and essentially it says what I presented you before. So it says that the cohomology ring of the rectangle arcing Lie algebra is a specific quotient of the exterior algebra on the generating space. Okay, I will not discuss about this, but what can be said about Bestina-Brady Lie algebras? So I could prove that a Bestina-Brady Lie algebra is Kojoule if and only if the flag complex on the graph is acyclic over the field. So I recall that the flag complex on a graph is the maximal simplicial complex having the graph as its one skeleton. So you have a graph, and then anytime you see a triangle, then you fill it with a simplex. Anytime you see a tetrahedron, then you fill it with a free simplex, and so on. This result here relates a cohomological property of the Bestina-Brady Lie algebra with a homological property of the defining graph, so to speak. And what I want to do now is to give you a proof of this fact. And in order to do this, we have to introduce HNN-extensions. Well, HNN-extensions in Lie algebra theory comes from group theory. In fact, the mathematicians Higman, Neumann, and Neumann, Bernard Neumann and Hannah Neumann introduced the notion of HNN-extensions in group theory because they wanted the aim of HNN-extension is to embed a group having two isomorphic subgroups into a larger group where the two isomorphic subgroups are also conjugate to each other's. The same idea can be translated into the Lie algebraic context, and we will see now how. So we need some data for defining the HNN extension, and these data are a graded Lie algebra, which is our base Lie algebra, a homogeneous subalgebra of the Lie algebra M, and finally a homogeneous derivation from the subalgebra A to the Lie algebra M. By a derivation, I mean a linear map that satisfies the Leibniz rule for the product. And by homogeneous, I mean that it sends, for some integer d, it sends elements of degree I into elements of degree I plus d. And okay, these are our data, and the associated HNN extension is nothing but the Lie algebra generated by the elements of M and a additional generator T. And we have to impose some relations. First of all, we want to impose the relations of M, and then we impose the relations for all elements of A. So we get a relation, the Lie bracket between T and that is our additional letter. The Lie bracket between T and A is equal to the derivation applied to A. So what we are doing here is to identify the adjoint map of T with a given derivation. So that now the derivation phi is comes from an inner derivation for the Lie algebra L. It can be proved that, for instance, M is naturally a subalgebra of L, and okay, yeah. In fact, recall that the adjoint map is a derivation. So here we are just identifying this inner derivation with a given derivation. Okay. HNN-extensions can be studied by a cohomology theory, and this was done by Kokhlukov and Martinez pairs again. In fact, they proved that there is a long exact sequence involving the bigraded cohomology groups of sorry of our data and of our HNN extension. And we will use this sequence a lot of time. Okay, so let's see an example that will be, in fact, the proof of the result on Besvino-Bradley algebras, but it is just an example so far. So we start with a very special case where the subalgebra M equals the subalgebra A. And we also assume that the derivation from A to M, so the derivation from M to itself, has degree 1. So that at the end, the additional letter will have degree 1. So we can form the HNN extension, and you can notice that I also wrote down this as a semi-direct product. This because in this situation here, there is no distinction between HNN extensions and semi-direct product. They have the same presentation, exactly the same Lie algebras. Okay, and now we want to assume that L is a Koszuli algebra. That I recall, it means that the cohomology group are concentrated on the diagonal. So what can be said about M? So we can write down the exact sequence, and we discover that the first and the last terms are 0 in this special case. This because of the causality of the Lie algebra L. And so we get an isomorphism between the mid elements in this sequence. So the H12 of M is equal to or isomorphic to H13 of M. Of course, we can try and change some more indices, and now we discover that the H13 of M is equal to H14 of M. And so what we get is an infinite chain of equalities between the non-diagonal pieces of the cohomology of M. We can do the same for higher internal degrees. And again, we discovered that for each homological degree, the non-diagonal pieces are all isomorphic to each others. And so the ith cohomology group splits as a direct sum of two factors. The first factor is, of course, the diagonal piece. And the second one is an infinite direct sum of equal pieces. Each piece is a non-diagonal homogeneous component of the cohomology. So, for instance, if the ith cohomology is finite dimensional, then the second factor must vanish. Yes. And this implies that if the ith cohomology group is finite dimensional, then all the non-diagonal pieces are 0. And so we have proved that if M is a homogeneous cocyclic ideal of a Koszuli algebra, then M is Koszul if and only if all of its cohomology groups are finite dimensional. And this is interesting because it relates a good cohomological behavior with just a finiteness property of the Lie algebra. And yeah, one can, for instance, apply this result to Bespina-Bredili algebra and see that the Bespina-Bredili algebra is cojoule precisely when it has finite dimensional cohomology groups. And this because of Robert's theorem, which says that L gamma is cojoule for all gamma. Yeah, in order to end the proof, we use this result of Koklukov and Martinez-Perez, which relates a finiteness property of the Bestina-Bredili algebra with some acyclicity of the flag complex on the graph. And so we get that B gamma is cojoule if and only if the flag complex is acyclic over the field. By the way, this argument can be used to compute the K cohomology for some field K of the Bestina-Bredi group of the graph. And this can be done by using the May spectral sequence, which relates the cohomology of a group with the cohomology of some of its associated Lie algebras. Okay. Do you have any questions so far? Okay. If not, I can go on with HNN-extensions. And okay, so far we have only introduced these HNN-extensions, and we have provided an example of its usage. Now we want to show two applications of HNN-extensions, which are somehow opposite to each other's. The first one says that any quadratically algebra split as an HNN-extension over any maximal standard subalgebra. So essentially, you have this is a fundamental lemma, although it is pretty trivial to prove, which says that you have a lot of freedom in decomposing any quadratically algebra over a maximal standard subalgebra. We will prove it later. And on the opposite side, the usage of HNN-extensions implies, the application of HNN-extension, you have that every finally presented graded Lie algebra embeds into some quadratic Lie algebra. So on one end, we have a quadratic Lie algebra, and we split it as an HNN-extension. So we are getting something smaller. And on the other hand, we are taking a graded Lie algebra and we are making it larger and larger with HNN-extensions. So they are somehow complementary procedure. Okay, so let's first see the general decomposition of a quadratic Lie algebra. So we can start with the arbitrary quadratic with a minimum representation of this form here. It is generated by x1 and xn, and the minimal relations are r1, rn. All the relations are of degree 2. So linear combinations of elements in x1, xn. So first of all, we fix a maximal standard subalgebra, which is a subalgebra that is standard, and so that its degree 1 component is one codimensional in the degree 1 component of L. So we can take it quite arbitrary among all the standard subalgebras of L. Then for all I, we can write down the presentation Ri as a sum of a bracket involving some elements of M and the element x1 plus a degree 2 element of M. So for instance, if the first relation is x2, x3, then x1 doesn't appear here. So the A1 is 0 and M1 is the bracket between x2 and x3. Okay, this is actually a sketch of the proof. One should take some free cover and do computation there, but in order to understand the proof, it is okay to see things at this level, at the level of the Lie algebra M. Okay, now one can define another standard subalgebra that is generated by the elements AI, which are by definition elements of M. So this will be a subalgebra of M. And finally, we define a derivation of degree 1. And this derivation here is defined so that, of course, in the HNN-extension, it will clearly equal the adjoint map of X1. So we put phi of A1 equal to minus Mi. And yeah, finally, the HNN-extension of this data is precisely the Lie algebra L. Okay, so as you can see, the proof is quite trivial, but the consequences of it are unexpected, I would say. So this is the HNN decomposition lemma that holds for all quadratically algebras. And so you take a quadratically algebra and a maximal standard subalgebra of it. Then you pick a degree 1 element that doesn't belong to the subalgebra M. And then you form the HNN-extension, which is isomorphic to the Lie algebra L. So any quadratically algebra splits as an HNN-extension. Okay, I want to give you now another example of a rectangular arc in Lie algebra in order to see a phenomenon, and then we will discuss how this phenomenon can be extended and treated by using HNN-extensions. This example is a bit different from the previous ones. It is a square graph. And in the rectangular arc in Lie algebra associated to the square, you can consider the subalgebra generated by these three elements. So we have x plus y, w, and z. It is not hard to see that the subalgebra generated by these three elements satisfies a relation which is clearly not of degree 2. And it is not hard to see that this relation here doesn't come from any degree 2 relation of the subalgebra. It comes from some relation of degree 2 in the Lie algebra, but not of the subalgebra. So we have found an example of a conjugate Lie algebra, the rectangular arc in Lie algebra, that contains a standard but not quadratic subalgebra. Okay. This suggests a definition. Actually, the motivation for defining this class of Lie algebras come from Galois theory, but I will not spend any word about it. So we will call a standard Lie algebra a bloccato Lie algebra if all the standard subalgebras of the Lie algebra are quadratic. So in the opposite case to this one, we have the bloccato Lie algebras. So bloccato means standard, and all standard subalgebras are quadratic. All right. Now let's see some examples of bloccato Lie algebras. Of course, you have standard abelian Lie algebras are locally abelian. So all standard subalgebras are, of course, abelian and so quadratic. Also, free Lie algebras, standard free Lie algebras are bloccato because by Kirchhoff-Witt theorem, the subalgebras of a free Lie algebra are free themselves, and so they are, of course, quadratic. And less trivially, and more generally, if A and B are bloccato, then both the free product of A and B and the direct product of one of them with an abelian Lie algebra are bloccato Lie algebras. Okay, so we can generate a lot of bloccato Lie algebras in this way. As a counterexample, if A and B are not abelian Lie algebras, then their direct product is not an abelian, is not a bloccato Lie algebra. And one example of this is precisely the rectangular arc in Lie algebra of the square, which is precisely the direct sum of two free Lie algebras, free non-abelian Lie algebras. Okay, so yeah, for right-angled arc in Lie algebras, we have this, let's say, translation of Drom's theorem that holds in group theory, which precisely characterizes those graphs for which the associated reg is a block-Lie algebra. For instance, a graph of this kind, this fish graph, has the right-angled arc in Lie algebra of this graph is block-Cato. This is a fish. Okay. Another use of, we are studying block-Cato algebras, and what can be said about block-Cato algebras? First of all, they are quadratic, but by using HNN decomposition, we can also prove that block-Cato algebras are also causal. And the proof is pretty easy. It can be done by induction on the number of generators. So we suppose that L is a block-Cato algebra, and we suppose that it is generated by a single element. Then, of course, it is abelian, and as we have seen, it is block-Cato. Now, if n is greater than 1, we can decompose L into the HNN-extension of an arbitrary standard subalgebra M with respect to a standard subalgebra A. Now, A and M are by construction standard subalgebras of L. And so in particular, all the standard subalgebra of them are quadratic. And in particular, M and A are block-Cato. And so by induction, A and M are both causal. So now we want to use the causality of the two terms A and M to conclude the causality of the algebra L. And this can be readily done by using, again, the exact sequence. We can write it down as follows. So we have the cohomology of A, the cohomology of M on the endpoints, on the termini of the exact sequence. And in the mid, we have the cohomology of L. So A and M are causal by point 4. And so if J is different from I, both the first and the last terms must vanish. And so the midterm must vanish too. So we get that the causality of M and A implies the causality of the algebra L. And so we are done, because this is what we wanted to prove. Oh, nice. So block-Cato algebras are, in fact, those causal algebras, so that all standard subalgebras are causal themselves. This is apparently much stronger than requiring the property of being quadratic and locally quadratic, so to speak. Notice that a similar proof of this result here applies to right-angled arc in Lie algebras, giving a different proof to Froberg's theorem. In fact, we can do the same by changing line 3 into M and A are not block-Cato, but right-angled arc in Lie algebras, and then all what follows is still true. Okay. Another application of HNN-extension, the HNN decomposition in the context of block-Cato algebras, implies that the center of a block-Cato algebra is always concentrated in degree 1. That is what I want to prove for causal algebras in general, but I couldn't. But at least for block-Cato algebras, we have this nice result that says that the center is not only concentrated in odd degrees and low degrees, but in degree 1. And in particular, it follows let's say, a Levy decomposition of any block-Cato algebra into an abelian term, direct product with an essentially simple ideal. So this is the block-Cato algebras are, let's say, centerless block-Cato algebras are essentially simple. By essentially simple, I mean that the intersection of non-zero ideals is a non-zero ideal. So they are not simple as Lie algebras, but they are not so far away from being simple, let's say. Okay, so we have done our part on the HNN decomposition. The last part of the talk will deal with the quadratic embeddings of graded Lie algebras into quadratic ones. So, for instance, the motivation for studying this comes from both group theory and Lie algebra theory. In fact, in group theory, the usage of HNN-extension allowed, I think Hickman was the first, to prove that any group embeds into a simple group. This is a nice theorem that uses HNN-extensions. Similarly, in the Lie algebra theory, Lichtman and Schiavani extended the proof to the Lie algebra realm, proving that any Lie algebra embeds, in fact, into a simple Lie algebra. But however, we are doing graded Lie algebras, and in the graded case, simple Lie algebras are not interesting. This because the only possible candidate for a simple Lie algebra in the graded context is the one-dimensional Lie algebra, which is not always considered a simple Lie algebra. And the problem for graded Lie algebras is that no non-zero Lie algebra is perfect. So the derived subalgebra is always different from the Lie algebra itself, because the minimal degree is 1, and the derived subalgebra is at least contained into the degree at least 2 of the Lie algebra. But anyway, I considered, let's say, as simple Lie algebras in this context, the quadratic ones. And in fact, I could prove that every finally presented graded Lie algebra embeds into a quadratic Lie algebra. Okay, so let's see. I want to provide you a proof of this fact, but only an example, and a pretty easy example. And the proof is just a generalization of this example, so to speak. So let's consider the easiest example of a non-quadratic Lie algebra. It is generated by the minimal possible number of elements, so 2, and it has a single non-quadratic relation. This is the easiest example. So we want to get rid somehow of this degree-free relation. And how to do? So first, we form an HNN extension, L1, by setting the additional generator T1 to act on the element X as the zero map. So T1 commutes with X, and we get a Lie algebra, L1. Now we can define another derivation from the subalgebra generated by X and T1 into the previous Lie algebra L1, which commutes with X, and which sends T1 to the Lie bracket of X and Y. This is readily seen to be a derivation because it sends relations to 0. By applying Leibniz rule, we see that the relations are sent to 0. And so we get another HNN extension, which in fact has a quadratic presentation. As you can see, we added two generators, T1 and T2, and the relations that we imposed make the previous relation unnecessary. It can be derived from the relations we have imposed. And as I said before, the HNN extension is an extension in the good way. So it contains the basis Lie algebra. And so we have produced a quadratically algebra starting from a non-quadratic one. So to recap the proof, we started with this non-quadratically algebra. We defined this new Lie algebra where the degree-free relation survives. And finally, we add another generator and some other relations. And from this relation, the first relation here can be deduced. So it is not a minimal relation for the Lie algebra. And so the final presentation of our Lie algebra L2 is quadratic, meaning that not all, but this particular kind of non-quadratic Lie algebra embeds into a quadratic one. In general, you can do the same. What you want to do is to add some more generators in order to get rid of some higher dimensional, higher degree relation. And yeah, the proof is not so complicated, but a bit technical. And I wanted to spend too much time on this. And I hope the example is enough. Just an observation before ending. It can be proved that this L2 is a Koszul Lie algebra. Clearly, it is not blockato because it contains a standard subalgebra that is not quadratic. So there's no chance that it is blockato. But still, it is Koszul. And my question to you is it always possible to embed a finally presented graded Lie algebra of finite cohomological dimension into a Koszul Lie algebra? Well, in principle, I thought that it was enough to suppose that finally presented graded Lie algebras embed into Koszul ones, but I found examples like the positive part of the Virasoro Lie algebra, which have infinite cohomological dimension, but still are finally presented. And of course, a Koszul Lie algebra cannot be of infinite cohomological dimension because its cohomology is a quotient of an exterior algebra on a finite dimensional vector space. So the cohomological dimension of a Koszul Lie algebra is finite, and so it must be that of all of its subalgebras. So nice. I want to leave you with this question here about the embedding into Koszul Lie algebras. And here is a set of references I used. In the first paper here, I introduced the notion of a blockato Lie algebra, while in the second paper here, which is still unpublished, I studied more the Koszul property for Lie algebras. And yeah, the aim of the first one was only to prove that block-Lie algebras satisfy a version of the Kurosh theorem, which is known to fail in general for Lie algebras. And the Kurosh theorem is related with the structure of subalgebras of free product. And for block-Lie algebras, you have such a theorem. And now the third and fourth references are Koklokov and Martinez-Perez that I cited before on the exact sequence from the HNN-extension, and it appears also the result about the Besvina-Brady Lie algebra. And finally, the last one is where Koszul algebras were first introduced in literature. And so thank you very much.
Thank you, Simone, for a nice talk. Are there questions? Well, if not, so let's
I
think.
I can
Let's
see a
yeah.
question in the chat. In the theorem
Oh
of
yeah.
Löfwall, what about the x1 component, the one component of x? Yeah. Let's see. Okay, here. Yeah, we wanted yeah, the question is about, I suspect that it is about the fact that I started the decomposition of x from x2. And this is due to the fact that if we have some relation of degree 1, then the presentation is not minimal. So we want that V is precisely the generating space, the minimal generating space for our Lie algebra. So if we have also some relation of degree 1, then some of the generators are not independent from the others. And this is why I started from a decomposition from the second homogeneous component.
Okay, thank you. More questions? Well, if not, thanks again for everybody for being present today and wish you a nice week. See you next Monday.
Thank you.
Goodbye.